So allow me to introduce myself. My name is Amanda Yo, and I am Delta Q's marketing specialist. I will be today's webinar moderator, and with some of you who are familiar with our company, Delta Q is a leading manufacturer of battery chargers for lead-acid and lithium-ion batteries. We provide power management and power conversion solutions that improve the performance and durability of electric drive vehicles and industrial equipment. Currently, there are 1.6 million electric vehicles that use our products today. On today's call, we have Chris Botting. Chris is Delta Q's Manager of Research, who is responsible for running our company's battery lab, which is an accredited efficiency testing facility. Previously, Chris was the Senior Systems Engineer at Azure Dynamics, where he led the integration of battery systems into electric and hybrid vehicles. We also have Brendon Sauer today, who is the Lithium Product Manager at Discover. Discover is one of many battery companies that Delta Q works with. They have extensive field experience that allows them to innovate and optimize and manufacture lead-acid batteries and lithium advanced energy systems for distribution through their knowledge-based sales and service network. We have invited them here today as Discover works in both lead-acid and lithium batteries and can provide an understanding of their experience in both markets. The main purpose of this presentation is to provide guidance to OEMs and distributors as they consider implementing lithium in their applications. To outline what we will discuss today, we will go over the benefits and challenges of lithium, case studies of lithium applications, what factors and components to consider when building a lithium system, and then we will leave some time at the end for questions. So, currently most industrial electric machines use traditional lead-acid batteries. As we go through the presentation today, we want you to consider your applications and whether or not it would be suitable for your products. OEMs are increasingly switching to lithium batteries, but why are they? So with this, I will hand it off to Chris to speak to the benefits and challenges.
Thanks, Amanda. So on this next slide here, we've laid out graphically some of the key benefits of lithium-ion batteries to answer that question of why make the switch. And the first thing to say is that there are many benefits, but those benefits aren't going to apply to all applications. So different applications are going to draw on different benefits. So the most noticeable feature of lithium-ion batteries is that they are lighter, much lighter and smaller than lead-acid batteries. That means that you can get the same energy out of a lithium pack that's up to 4 times lighter and up to 3 times smaller. Or if you choose, you can pack much more energy into the same space, giving you longer machine runtimes and vehicle range relative to lead acid. Now, lithium batteries can also deliver higher power, which can give you higher performance vehicles and machines. So that's the top row, and you can see how that would be quite critical if you're making a performance or power sport vehicle, something that needs longer runtimes, lighter, higher power. Moving to the bottom row, this is more about productivity and operating cost. So lithium-ion batteries also have big advantages when charging. They can charge much faster, and less charging time means less downtime and more productive vehicle uptime. They also charge much more efficiently and reduce energy bills, typically 10 to 15%. Now, unlike wet lead-acid batteries, lithium batteries are sealed. There's no acid and corrosion. They don't require labor for maintenance and watering and equalizing. So that's a savings. And last, but certainly not least, lithium-ion batteries have much longer life than lead-acid. It'll depend on the make and model, but typically thousands of cycles instead of hundreds of cycles. So they can last many years without replacement and warranty costs. So to sum up, lithium-ion batteries can give you higher performance and higher productivity with lower operating costs. Now, let's look at some specific case studies to see what lithium-ion's value proposition is in some different applications. Our first case study is fleet golf. Now, just last month, EasyGo, a leading maker of golf cars and utility vehicles, launched a new series of vehicles that replaces their traditional lead-acid battery packs with lithium-ion packs from Samsung SDI. Now, Delta Q works closely with E-Z-Go. We're the battery charger supplier for both the lead acid and the lithium cars, so we can give you the inside view here. So what value does E-Z-Go see in moving to lithium? What's their motivation? First, the longer cycle life of lithium-ion lets E-Z-Go offer a longer warranty, longer than any warranty currently offered in the fleet golf market. And this is critical because battery warranty is a key competitive metric in the golf market. They compete head-to-head on battery warranty. And because many golf cars are leased instead of being bought, the longer life means that at the end of lease you have a higher residual value for the battery pack and the vehicle, which in turn lets you offer more competitive leasing terms. Now, that's certainly one of the main benefits. E-Z-Go also points to faster charge times and to reduce energy bills. There's no battery watering or cleaning, which means maintenance cost savings, which can be a substantial saving for a large golf course with a fleet of 100 or 200 golf cars. And finally, the lithium cars weigh hundreds of pounds less, which reduces wear and tear on golf greens, which are a pretty valuable and delicate asset. Now, moving on to a second case study, let's look at forklifts. Class 3 pallet trucks or walkies, they traditionally use lead-acid batteries. But lead-acid batteries have long charge times, and that makes it hard to keep up in a fast-paced warehouse environment. So in a busy distribution center that runs 24/7, that runs 3 shifts, you would typically need to have 3 battery packs for each forklift. So you've got 1 battery pack per forklift per shift. And you also need dedicated floor space and heavy equipment for charging and for swapping in fresh packs. So in a typical machine, a pack would be depleted in 1 shift, and then it would spend the next 2 shifts charging and resting and cooling so it's ready for the next day. So obviously that's a lot of floor space and manpower and capital which is tied up in battery charging and changing. That's a major pain point. So some suppliers are turning to lithium-ion to solve this pain point. Lithium-ion can run much longer and charge much faster without a cool down rest period. And you can fast charge or opportunity charge while the operators are on break, and that may let you use the packs continuously without needing battery changeouts. That's a big game changer. Getting rid of battery maintenance is also an important labor and cost saving. Now, interestingly, this is one application where the lower weight isn't necessarily an advantage. In fact, some counterbalance lift trucks actually rely on the heavy lead-acid battery for ballast. So if you switch from lead-acid to lithium, you may actually have to add back in some of the weight that you've removed in the form of lead weights. Now I'll turn it over to Brendon to look at a third case study.
Thanks, Chris. Today I'll just introduce somewhat of a generic industry-wide use case, focusing on the scrubber sweeper market. Now, as we've discussed in the past 5 or 10 minutes, there are a number of useful features and benefits that lithium can provide. Some manufacturers may choose to rely on all of them to add to their value proposition, or some will focus only on 1 or 2 hot buttons. It really boils down to productivity enhancements, though. How can your equipment offer more value to the end user? One of those key aspects is runtime. Now, really, with lithium, you've got 2 scenarios that you can think about. One, you can offer significantly more runtime by directly replacing that lead-acid pack with the same volume of lithium pack. Some people may find that this is actually too much runtime. The equipment runs longer, the motors run longer, there's just more hours tallied up. Now, alternatively, you could evaluate offering the same runtime or marginally more with a smaller lithium pack. which offers you the flexibility to add in more water, more chemicals, or whatever else you may consider a valuable asset that you just can't get enough of in your equipment today. Now, I'll talk a little bit about why you can use a smaller lithium pack and achieve the same run times in the next slide. Let's move on to charging. Fast charging seems to be a fairly hot topic these days. And typically, the only way to achieve it with lead acid is to install larger chargers, more cost. They produce or output more current, your batteries run hotter, and ultimately, there's a reduced lifetime on your lead acid batteries. With lithium, you can charge within 2 hours and have no effect on the lifetime of the battery. And that sometimes can be achieved using the same charger or the same charger size you're using today. You're free to opportunity charge at any time for as long as you want. So I know with lead there may be restrictions. If you're going to opportunity time, there may be a minimum amount of time. It's kind of analogous to your phone. So if you need 10% extra SOC, you go plug it in for 15 minutes. Feel free to do that with lithium without impacting the life of your pack. Also, useful life is something to consider. Typically, a lithium pack should last for the life of your equipment. So we're not talking about swapping out packs every year or 2 years. You should be able to achieve at least 5 years and thousands of cycles when using lithium. So let's move to the next slide here. Now this slide is fairly cryptic and it probably deserves a webinar in and of itself. I've tried to graphically show the capacity that a lithium system and a lead system will deliver at various currents. So the blue bubbles represent lead, the green bubbles represent lithium. Most lead acid packs, their data sheets are published at 100% depth of discharge, and there's a number of capacity ratings. It could be as high as a 120-hour rate right down to the 1-hour rate. So a lot of people and battery users will refer to their lead acid batteries at the 20-hour rate, which is more to the left of the spectrum here. So you might need to discharge at 1.3 amps or 5.8 amps to actually achieve that 20-hour rate. This industry, the scrubber sweeper market, is typically operating between, let's say, 30 to 90 amps towards the right end of the spectrum. So as you pull more current from a lead acid battery, it will deliver less and less capacity. This is really due to the internal efficiency of lead acid. It's typically only about 80%, whereas with lithium, that's upwards of 95%. So within this graph, it kind of summarizes the need to oversize your lead, typically because you should only use about 80% of its capacity if you want to maintain a healthy lifetime. And you typically also need to oversize your lead because of its low internal efficiency. And one more quick case study I did for everyone out here, just to speak again to charging. I, in preparation for this webinar, did a quick little test in our lab. I took a lead acid pack, using 2 EV12 8-A's and in series for a 24-volt configuration, and paired that with a lithium pack, our 1424 2800. From both packs, I discharged 72 amp hours, and I used the same charger with application-specific algorithms. So with the same charger, you can see that lead acid took significantly longer. And there's a bit of a caveat here. I did use a pulsing algorithm, so you could probably take 2 to 3 hours off of that lead charge. But regardless, same charger, same scenario, you can see that lithium, we were able to charge it at least 50% faster than lead. And with that, I will hand it back to Chris.
Right, so that all seems pretty compelling. You can charge faster with less energy and pack more power into the same space. So why isn't everyone using lithium-ion today? Well, there are some negatives, and it's important to be aware of them, that there are some challenges with using lithium-ion. The big one, the one that you'll run into first, is the upfront cost. So today, a lithium-ion battery pack can cost four to five times as much as a lead-acid battery. Now, this is improving. Lithium-ion costs continue to come down every year at a pretty predictable rate. And this can also be mitigated. Just because a lithium-ion battery might cost 4 or 5 times as much for the same amount of energy doesn't mean that you need to put in as much pack. So you can mitigate this by using a smaller lithium pack. Because lithium-ion doesn't derate or degrade nearly as much as lead-acid, as Brendon walked us through, you don't have as much derating based on charge rate. You don't have as much degrading with age. So you don't need to oversize a lithium-ion pack nearly as much as you would typically oversize a lead-acid pack at the beginning of life, so that you get the performance and capacity that you need at end of life. So you can mitigate this, but still there's a higher cost up front. Now, the other two challenges are related. Lithium-ion cells can be thermally volatile if they're abused or if they're used outside of their safe operating area. So that's an issue. To avoid unsafe operation, all lithium battery packs require a battery management system, a BMS. So this adds complexity and it adds cost. Let's look at this issue in more detail. So if you've been paying attention to the news in recent years, you'll know that lithium-ion batteries have had some safety challenges. Let's say that this is a hot topic. In the last decade, we've seen highly public fires and recalls of consumer electronics, laptops, toys, vehicles, and phones, and even airplanes. Now, let's put this into context. All forms of energy storage have some risk. You can't store a bunch of energy in a small space without having some risk that it gets released in a way that you don't want it to be released. So gasoline can ignite, and compressed air tanks can rupture, and even dams can burst. With most mature storage technologies, we understand these risks, we accept them, and we manage them with well-understood safeguards and best practices and safety margins. Now, lithium-ion batteries are fundamentally no different. They have risks, but they can be managed, and the problems generally occur when the quality and the safety margins are compromised because of competitive pressures which demand the lowest possible prices or the highest possible energy density. So if you're trying to make the cheapest hoverboard that you can, if you're trying to squeeze as much capacity into a phone as you can and you start cutting corners, that's where the issues come in. But nevertheless, lithium-ion batteries are objectively more volatile than lead-acid batteries. So let's look at exactly why that's true. To understand the lithium-ion failure mechanisms, we need to look at how the battery is constructed. I'll just draw your attention to a few details in the diagram on the right. We don't need to look at all of it, but on the far right there you'll see several layers, the anode, the cathode, and between them the separator. And please hang in with me, I promise that there won't be a test. Voltage is generated between the electrodes called the cathode and the anode, which is the positive and the negative of the cell. Unlike in a lead-acid battery, these aren't thick, rigid plates. Instead, they're thin films pasted on metal foils, think aluminum foil, and they're separated by a porous plastic film called the separator. Think really, really thin white plastic like a kitchen garbage bag. The separator is wetted with a conductive liquid called the electrolyte, which allows the ions to flow between the positive and the negative. Now, with lead-acid batteries, the failure modes are relatively benign. In a lead-acid battery, you've got these electrode plates that are big, they're rigid, they're well separated. The separator is thick, and it's all bathed in a water-based electrolyte. So which is non-flammable and has lots of heat capacity, and fundamentally you can't set that water on fire. So if you aggressively or abusively overcharge or overheat a lead-acid battery, you can lose water and dry it out. You can generate hydrogen gas, and you can melt the lead terminals, but the hazard is limited. So what can go wrong with lithium-ion batteries? Why is it more volatile than lead? So the positive, or cathode, is a metal oxide. And if you overheat it or overcharge it, it can break down and release oxygen. The anode, or negative, if you charge it too fast at cold temperatures, you can plate metallic lithium, which is highly reactive. If the separator is overheated, so it melts or softens, if it's crushed or punctured, then it can allow the anode and the cathode to short to each other. And the electrolyte itself, it's an organic solvent and can be highly flammable. So you've got a potential oxygen source, you've got a potential fuel, and a potential source of ignition all together in a sealed container under pressure. And many of these factors will increase over time as the cell ages and as it builds up in the as it builds pressure over time. Now, in practice, these failure modes are relatively well understood, and they can be avoided by keeping the cells protected and within conservative, safe operating limits. So this includes limiting overcharge and limiting discharge. It includes limiting charging when it's too cold and operation when it's too hot. And the cells should also be protected from physical abuse, which would include external short circuits and crush and puncture. Now finally, even when a cell is protected and safely operated, it can still have an internal failure due to manufacturing defects. Now, this is avoided by proper cell design and by manufacturing quality controls. So let's take a look at what this means in practice for battery design. There are real risks to lithium-ion, but they can be mitigated by proper system design. There's no rocket science here. It's fairly straightforward, well understood system design principles. A safe design starts from the bottom up. So I've got an inverted pyramid here to show that you move from, you build in safety from the lowest level of assembly, which is the cell, and you cascade up to the higher levels of integration. So cells are built into modules, modules are built into a pack. The pack is wrapped in a case, integrated with a system, including battery management and cooling and a charger. And at each level, you consider safety, you consider the impact of single points of failure. Let's walk through this step by step. So the first step is to select the battery cells. The cells are the basic building block of the pack. Battery cells are not one size fits all. We often get questions about what cell should I use or what chemistry should I use. And the answer is there isn't a single answer, and it depends on your application. So finding the right fit for a specific application, it just involves understanding a number of different trade-offs and considerations. We're just going to breeze through these at a high level. So first, the geometry. Cells can be cylindrical, so think AA's and AAA's. Cells can be prismatic or rectangular, or they can be thin laminated pouches, which is what's used in cell phones and tablets. So each of these geometries has different costs. It is different packing densities. You can imagine that if you're packing a bunch of rectangles into a space, you'll have less wasted space than if you're packing a bunch of cylinders into a space. And these geometries also will have different terminal connections, and they'll have different stability for aging and pressure changes. Now, size can vary quite a bit, from little AAA cylindrical cells, which just might weigh a few grams, to very large prismatic cells, which might weigh a few kilograms each. And this is another of these trade-offs. If you choose a small cell, you're going to need many more of them, which means many more interconnections and a lot of packaging, which in turn means that you have more failure modes. But it also means that because the individual cells are small, you have limited thermal energy in any one cell if that could be released if a single cell fails. Now, by contrast, if you use a very large cell, that's going to lead to a simpler design. You're going to have less cells, which means less interconnections and less failure points. But, and this is important, larger cells have more thermal energy in them. So if one fails, that's going to be a more dramatic event. And also, larger cells are harder to cool. There's more thermal resistance from the inside of the cell to the out. And if the cell is harder to cool, that has implications for safety. It also has implications for life and performance. Now, a key decision is the chemistry to use. So if you're new to lithium-ion and you're wondering, what do you mean, which chemistry to use? I'm talking about lithium-ion. Well, lithium-ion isn't monolithic. It's more like a family of different chemistries or different flavors, which we typically identify by the cathode or positive material. So the main trade-off here is going to be between energy density and thermal stability or safety. So we've listed some of the more common chemistries, and we've placed them on a continuum. So from left to right here, to the left, the energy density gets higher. So at the left, you have cells that are smaller and lighter, and so they're also potentially cheaper for a given energy. And to the right, you get improved thermal stability, which decreases the safety risk. So for context, consumer electronics generally use the oldest chemistry, LCO, which is at the far left. So this packs a lot of energy into a small cell, but it has a higher fire risk. And so if we were to go back to the slide where we showed those examples of product recalls, to the best of my knowledge, all of those cells are using LCO, the oldest chemistry, which is also the most volatile. Most automotive electric vehicles today will find a sweet spot somewhere in the middle of that spectrum. And there's some consensus emerging around NMC, or nickel manganese cobalt oxide, which is going to find use in vehicles like the Chevy Volt and Bolt. Now, further to the right, you've got LFP, or lithium iron phosphate. This is also a common chemistry. It's commonly produced in China, where it's used in large cars and buses, among other applications. Now, finally, and this is maybe the most important point, it is imperative to source cells that are consistent, that have consistent high quality. Manufacturing lithium-ion batteries isn't like making lead-acid batteries. It's much more like semiconductor fabrication. So if you can picture workers in a semiconductor fab wearing the white bunny suits with the booties on their feet to protect against any particle contamination, they'll be going through double airlocks with positive pressure to make sure you don't get any contamination into the manufacturing area. Be highly automated to just get humans out of the process. So manufacturing lithium-ion batteries requires really tight control of air contaminants and humidity, and the very high purity of the materials and process tolerances and cleanliness. Now, this all drives cost, and this is one reason why lithium-ion batteries are more expensive than lead-acid. But the bottom line here is that you need to select a battery make with a really solid reputation, with a track record for best-in-class manufacturing quality control. Now, I'll hand it over to Brendon to talk through how Discover did their cell selection.
Thanks, Chris. I'll just take this quick opportunity to encourage everyone out there to send in any questions you may have. So we do have 15 or 20 minutes towards the end. And I think that'll be a valuable exercise for everyone if we have some good questions. Discover produces batteries for many applications. At the end of the day, we can't be certain where our batteries go. When you're designing a laptop or a cell phone, the use case is pretty well understood. So you can design your batteries to be suited for all the worst case scenarios that you could dream of. Whereas we sell batteries in different environments. They have different performance requirements, whether that's currents, voltages, temperatures, different mechanical stresses. So really, Discover's driving motivation when selecting our cell chemistry was to pick the most stable one out there. The most inherent safety. We wanted to eliminate as much of the risk as we could. And as such, we chose lithium iron phosphate. We believe that it is the most stable chemistry available today, and so far we're quite happy with it. We also selected a cylindrical cell, and this offered us a large flexibility and ease of integration. So we can take that same cylindrical cell and connect a number of them in different configurations to offer different pack sizes. We also went with a screw terminal type, so we screw our cells together as opposed to welding them. And this allows us to pull more current, and there's less thermal stress. So in some of our earlier testing, when we tested welding cells together, we found that it just couldn't carry as much current as we needed. Now, quickly, there are some different characteristics with each chemistry. They all have different nominal voltages, so some may be 3.7 volts nominally. Lithium iron phosphate is actually 3.2 volts nominally, and that lines up quite nicely with lead acid when you take our cells and put them in series. Well, interestingly enough, lithium iron phosphate has a really stable voltage curve. So on this graph here, I did a few tests once again, lead acid versus lithium being the green lines, at different discharge rates. So anywhere from 1800 watt discharges to 3600 watt discharges. And you can see that that lithium discharge curve is really flat and stable. What does that mean? It means your motor is going to run cooler, there's less wear and tear on your electrical components, and most importantly, the user is going to experience the same performance from the start of shift to the end of shift. So you won't see that kind of decaying run or motor speeds. Your lead acid might slowly die, your equipment gets slower, the brushes turn slower. Lithium iron phosphate will just go until it stops. With that, I'll hand it back over to Chris.
Right, so we've looked at the cells, and the next level up from the cells is the modules. So modules are made up of series and parallel connected cells to get to the voltage and the capacity which you want for a packed building block. Now, cell terminals have to be connected electrically in a way that is reliable, that is repeatable, and is low resistance. On smaller cells, this is generally done by welding, laser or ultrasonic welding. On larger cells, they're more likely to have threaded screw connections whose torque must be carefully controlled. So as Brendon highlighted, they've selected cells which have screw connections. Now, you also need to physically constrain the cells. They just can't be rattling around. They have to be held in place by some sort of structure. And that structure has to be able to tolerate high mechanical shock and vibration g-forces. And that means that it's important how you hold the cells, whether you're holding the body of the cell or the terminal of the cell, and this can become really important when you have large, high-mass cells, because you don't want them to shake themselves apart in the application. So packs are then built by connecting modules in series and sometimes in parallel. The pack case that you wrap around it should keep out contaminants like dust and water, which are not going to be good for electronics or for batteries. You want your case to prevent physical access and mechanical abuse so that nothing penetrates or crushes the cell. And your pack needs provisions to mount into the vehicle or machine, so some sort of bolt connections or other mounting. Now, the module and the pack level is also where decisions are made about cooling. In many of the industrial applications that we're talking about, cooling will be entirely by passive convection. So you're not adding moving parts which can fail. You're not adding liquid coolants which can leak. It can be quite simple and cheap. But if you want longer life in hot climates, or if you have an application where you're going to have heavy, high power, high duty cycle use. So for instance, if you have a forklift and you don't want it to have to swap batteries and cool, and you're going to fast charge it and use it continuously, you may need to get more heat out. And if you need to get more heat out, then you start moving to forced air, so fans, or even to liquid cooling. Cooling is not only to remove heat from the cells, but it's also to reduce thermal gradients in the pack. So the basic challenge is that cells that run hotter are going to age faster. They're going to degrade faster and lose capacity and power. So you want to keep the cells cool. So if the whole pack is hot, the whole pack is going to degrade faster. But it's not enough to keep the pack cool. You also want to keep the temperatures consistent throughout the pack. Because if you have some cells that are running hotter than other cells, those hot cells are going to age faster. And that uneven aging leads to uneven capacity and resistance, and then the weak cells can limit capacity and performance and life. So just moving on then. The module on the pack level is also where the battery management system, or the BMS, is integrated. There are many different BMS topologies. BMSs can look quite different, but they'll all be printed circuit boards that have some electrical connections to the cells that they monitor and control. Sometimes this is a centralized architecture where you've got one big printed circuit board and it's got a wire harness connecting to all the cells. In some cases, it'll be at the other end of the spectrum, you'll have an entirely distributed system instead of a centralized system. So you got lots of little circuit boards attached to individual cells or groups of cells. Typically, you see something in the middle. At these sort of pack sizes, you typically have a master BMS controller, and then you have slave modules that are distributed through the pack to monitor groups of cells. But regardless of what the BMS looks like, all battery management systems should have the same core functions. They all need to monitor and estimate and manage and protect. So let's just walk through those at a high level. All series cell voltages will be monitored, as well as pack temperatures and voltage and current. So that's a lot of information to be monitoring at the cell level. And from this data, the state of charge is estimated, so how full the tank is, as well as state of health, what is the age and the health of the pack, and allowable charge and discharge power limits. How hard can you use the pack? The BMS then uses this information to manage the battery. If the cell voltages or states of charge deviate too much, then the BMS will use cell-level hardware to balance the cells, to bring down the cells that are higher or to bring up the cells that are lower so that they're all at a consistent voltage and state of charge. The BMS may also limit use. So if the state of charge is getting out of range, if the battery is getting too hot or too cold, if you're starting to move outside of that operating area for safe operation or just for long life operation, the BMS will limit battery use by communicating with or controlling other system modules. So the BMS may tell the motor controller to limit how much current it draws. The BMS may tell the charger to limit how much current it puts into the battery. And the BMS may also communicate status to to the end user by a display to warn of fault or limiting conditions. Now finally, and probably most importantly, the BMS must be able to protect the cells by electrically disconnecting them from the system. So if the BMS isn't able to keep the pack in a safe operating range by controlling or communicating with other devices, then it'll its last resort, its last line of defense is to simply disconnect from the system. So one final point on the BMS, and this is important, it must be an integral part of the battery system. The BMS may be sourced separately. The hardware and software may be developed by a different team or a third party. But it's not something which can be integrated in isolation without any consideration of the needs of the cells. The BMS should be developed or integrated in close collaboration with the cell maker, because it's very important that you've got a proper understanding of that safe operating area and what the limits are to ensure long life. So finally, the battery pack must be integrated into a system, and that system includes a charger. Charger integration is often an afterthought, so people focus a lot on what cells to use, what battery chemistry to use. They'll build the cells into modules and packs, and they'll wrap a case around it, and they'll integrate cooling and a BMS, and then often the charger is the last thing which is thought of. But charger integration is actually quite important. It can have a big influence on battery life and safety and performance, and here's why. So the first decision is the charge algorithm. So this is how to charge, how fast, how much, and when. So the charge algorithm is can look deceptively simple. It's often constant power or constant current followed by constant voltage. But this must be carefully tuned to strike the right balance between runtime and charge time and life. Let's talk about why that is. So we've already said that lithium batteries will age faster if they're hot. Lithium batteries will also age faster if they spend more time at high voltages and high states of charge. So for this reason, battery packs, you typically don't charge them to their theoretical maximum charge. You don't cram in all the energy that you could, but you limit to a reduced state of charge target. And the art is to carefully select that target. If that target is lower, you'll get less runtime from the battery pack on each cycle, but you'll have a longer expected pack life and warranty because you limit the time spent at high voltage and high states of charge. So the way that you would charge a cell phone that needs to have a 2 or 3 year life versus the way that you charge a machine that might need a 10-year life, that's going to be quite different. You'll be more conservative to get longer life. Charge rates may also be tapered or reduced to limit heating in the cells, which again is accelerating aging. And charging will be restricted or even disabled at low temperatures to avoid lithium plating. Because if you get plating of the metallic lithium, you permanently lose capacity and you may also raise the safety risk. So these are all considerations. Now, the BMS, the battery management system, needs to be actively involved in this process. So typically there's some form of communication between the BMS and the charger to control the charge. This can be a serial protocol like CAN bus or Modbus or LIN or SPI. This could be an analog or a pulse width modulated signal. It could even be a simple discrete on-off signal to enable or disable the charger. Another consideration is the charger's output waveform or charge quality. So not all chargers are created equal. If you have a 10 amp charger, that could mean that you have a nice clean 10 amp DC with no ripple, with no noise, but it could mean that you have high noise. It could mean that you have an average current of 10 amps, but you have 100% current ripple because there's no filtering from the AC line, in which case your root mean square or your RMS current, which is what drives heating, will be higher. So if you've got poor power quality and high current ripple, that can increase heating in the batteries, which again has a life impact. And you can also create noise on the BMS's cell voltage measurements, which may limit, may cause false positives or limit the operating area. Now, voltage control, accuracy and control stability are also very important. They're critical for performance, life, and safety of lithium-ion. We were talking about how you've got to have a trade-off between how much energy you decide to cram into the cells versus how much life you're going to get out of them. And this is where it's particularly important to control the voltage. And this is actually very true for the LFP chemistry that's used by Discover, as we found in our testing. And then finally, a battery charger should have reliable hardware and software. The charger has to be durable. It's in the same harsh application environment as the battery. So the software design and verification should also be done to ensure that the charger follows the desired algorithm and that it responds to the limits that are communicated by the pack's BMS so the charge can be controlled. Now, I'll hand it back to Amanda to wrap things up.
Okay, thank you, Chris. Before we head into the question and answer period, we will review some of the key points from today's presentation. So lithium-ion has a compelling value proposition in specific applications. So obviously you want to take that just to see back to your team, just to see what we had gone over today and see if it's suitable for yours. The safety risk is real and can be mitigated by proper system design and quality control. Another key point is that the BMS is an integral part of the lithium system and should be developed in close collaboration with the cell maker. And of course, the charger cannot be an afterthought. It must be integrated to ensure performance, life, and safety. We often find that sometimes that people consider it as an afterthought, but the lithium system should be considered as a whole. So, just a few things before we head into the question and answer sections. We're just going to let Chris and Brendon here just kind of review some of the questions that we've gotten, because it seems like we have quite a few today. So before we head off that, so first question there, guys.
All right, well, we're just looking at a very long list. I think some questions may rely on personal opinion and whatnot. We're going to try to shy away from that and give everyone the most unbiased answer we can. So the first question we want to talk about is to achieve maximum life, what is the depth of discharge that is allowed?
Yeah, this is going to really depend on the cell and the application. So, to be clear, if you take a commercial cell and you put it in a cell phone where you've got one cell in that phone and you've got a design life of 2 or 3 years before someone gets a new phone, you're going to cram as much energy. You're going to use as much energy as you can to give long run times, and your life will just be a few years. If you're putting it in a car, it's got to have 10-year life. That's going to be, so it's going to be a trade-off that's specific to the application and to the chemistry in the cell. I don't think that we can say a specific number that just applies across the board, but for sure, if you want to maximize life, you're going to limit how high you charge, how low you discharge, and you're going to also want to limit maximum temperatures.
So I think I'm going to try to jump ahead and answer 2 or 3 questions at once here that relate to this. So further down the list, someone had asked how the BMS might prevent or monitor depth of discharge, and whether or not you should use an internal BMS or an external BMS. So as it relates to Discover's packs, it's an integrated system. You're buying the entire battery. It comes with the BMS. It comes with the certifications. So we cut the discharge off for a number of reasons. High temperature, low temperature, currents, voltages. As it relates to depth of discharge, we will open the battery's internal protection switch and cut you off when the voltage gets too low. So we do leave a little bit of depth of discharge or a little bit of capacity in the battery. So on our end, we ensure that the customer or the user cannot abuse the battery. That's the whole point of the BMS. And that's why it's so important that it's internal to our system. We don't offer people the opportunity to go and select their own BMS and kind of play with these numbers. We've worked for a number of years with the cell supplier, with the certification agencies, and with testing to determine what the best numbers are.
Yeah, so just looking at some more of these questions. There's a question, can you mix AGM or sealed lead acid batteries with lithium ion? You could. I've seen people try to build hybrid energy systems with cheaper lead-acid batteries for capacity and lithium-ion or ultracapacitors for high power and long life, and it doesn't usually end up working out. It looks good on paper, but by the time you start looking at the electronics or DC-DC converters that you need between the two energy systems, I wouldn't recommend it. If a single cell in the pack was to go bad, is it repairable or does the pack need to be changed? This is going to get at the trade-off between using lots of small cells versus using a few large cells. If you're using a few large cells, you may be able to, physically unbolt the cell, take it out, drop a new one in. But at the same time, with large cells, you're going to be more affected by a bad cell. If you've got a pack where you've got lots of small cells in parallel, you probably can't change them out because they'll all be welded together or integrated in a way that it's not practical to change cells. You're more likely to replace a module or even the whole pack. But if you have bad cells, you generally don't need to replace them, because if you have a bunch of cells in parallel and one is weak or even two is weak, you typically won't notice.
Yeah, the battery will kind of take care of itself.
Yeah.
Quickly, I see a question here about benefits of lithium for solar usage where size and weight is not a concern. Well, I think typically when we look at the renewable energy market, we think of usable capacity. So if you want your lead acid batteries to offer a meaningful, useful life, you should only use maximum 50% depth of discharge. So you need to install double the system you actually require.
Yeah.
And that doesn't take into consideration lead acid degradation. So if you've got a 25-year design time, maybe you're up to 2 or 3 times as much capacity as you need. With lithium, I don't think you need to consider that derating factor.
Yeah, and I would say that the size and weight aren't a concern. I just say that they're less of a concern, but certainly ask the guy building the system and carting in those 1,000-pound lead acid batteries whether it's a concern. But there's a couple of pretty key benefits here. Well, life is going to be a huge benefit just in looking at total cost of ownership, but also the round-trip energy efficiency of lithium-ion is going to be much higher. So, I think we had said previously with lead acid, you're talking 80%. With lithium-ion, you're talking 95%. And those are real numbers that I've seen in my lab. You can see a 15, even a 20% energy efficiency difference. And then the other key difference is that lithium-ion batteries really do not mind sitting forever at a partial state of charge, which is what you want for a renewable application.
They might actually prefer it.
Yes, yeah. Like they're going to actually last longer sitting at a partial state of charge than sitting fully charged. Now, lead acid, if you don't frequently fully charge them with a nice, gentle, long charge profiles to break up those lead sulfates, they're going to have a short life. And that's not going to work well for like an off-grid solar application.
We have another question here that asks if you can briefly describe how the charging is different between lead acid and lithium, and how the BMS comes into play.
Chris had said earlier, it may seem like charging lithium is rather simple, and I think it is, but it requires tighter tolerances. So we're really after nice voltage limits. We don't like to see those deviate. So if the voltage is a little bit too low, you'll see a bit of a reduction in capacity. And on the high side, we don't want to see it get too high because you start to abuse the cell. And in our case, the BMS will step in and just stop the charge. That results in a user experience that's not very nice and clean. When we don't have communication with the charger, we recommend a more conservative charge voltage. So that leaves a little bit of capacity on the table, but kind of takes away any abuse from the equation. Whereas if there is communications, the BMS can request the exact voltage and current that battery needs at that given time. So I'll let Chris talk to that a bit more.
Yeah, no, I think that's the key point. I would also add that with the same charger, you can typically charge a lithium pack somewhat faster, like maybe 10, 20% faster than a lead pack. And actually, that can be a much more dramatic time difference. So we recently ran some tests, actually just last week, looking at very large lithium packs versus very large flooded lead acid packs. And we found that not only is the lithium pack much more efficient to charge, but you can charge the same size pack in, I think it was about 2/3 of the time. So it's a significant reduction in the charge time. So with the same charger hardware, you can get a faster charge, or of course you can use a higher power charger and charge faster. Like 4 hours is going to be a very fast charge for a lead acid battery, which is potentially limiting life. But you can charge lithium in under an hour if you really want to.
Quite aggressively.
Yeah.
That segues nicely into, someone asked how much heat is generated when charging. I think this is totally going to depend on the size of your pack and the size of your charger. Anecdotally speaking, with our systems in our test lab, they typically cool down when we charge. So that's because we pull them right off of a discharge, and the charger's current is lower than the actual discharge current. So it's kind of a relaxing time for them just to settle down, and they actually they cool down.
Yeah. Yeah, so I'd say, I mean, there's really three factors here. There's how much heat are you generating in the cell, how much heat capacity is there, and how fast can you get the heat out. So different geometries are going to have different impacts there. So for sure, with lithium, you're generating much less heat. Maybe you're generating half the heat or less. But keep in mind, lead acid batteries are big. They contain a lot of water. That's a lot of heat capacity. So if you put the same amount of heat into a lead battery or a lithium battery, the lithium battery gets hotter. Now, you can also typically get heat out of small lithium cells faster. So there was a comment here that AGM batteries may not get as hot as wet flooded batteries. And for sure, you're losing more energy, generating more heat in a flooded battery. But when a sealed AGM battery gets really hot, it takes a long time to cool down.
Another good charging question. Why do you want your lithium batteries to heat up before you charge? And that goes back to, it's just kind of an abuse situation. You're hurting your battery when you're charging it at low temperatures. And that's kind of at the chemical level. So Chris was talking about lithium plating at those temperatures. It's just not a good idea to charge your batteries at a cold temperature.
Well, we only have time for maybe one more question. We're just going to take a look through the additional questions that people have sent in just as we've been talking here. And
I guess keep in mind, I believe our contact information is up there, so you can also send your questions to our emails if we didn't address them today. Chris is just picking the juiciest question.
Yeah, so there's a question saying that you can parallel packs to get more capacity. Why can't you connect packs in series? That's going to be a function of how the electronics is constructed. There's no reason why you can't put cells, any number of cells, in series or in parallel. But in terms of the electronics, it's usually very simple to parallel them. We're actually running a number of Discover packs in our lab right now paralleled. But if you're going to put them in series, then you would need to design the electronics to handle that higher voltage. And the packs can't share and automatically balance themselves. If you take a fully charged and a fully discharged lithium pack and you connect them in parallel, that will eventually work out. The fully charged pack will take more discharge current and less charge current. But if you connect them in series and they've got the same current flowing through them, there's no opportunity to balance that difference.
Exactly. So really, I see that question a lot. Why can't I place these batteries in series? And fundamentally, it comes down to the BMS is not designed for it. That's why we offer packs at system voltage that allows us the opportunity to design the electronics for that system voltage.
okay, well, that will probably just be our last question for today. As we close out our webinar today, we will leave you with a couple of resources which you can definitely go through a little later. These are papers that we thought would be interesting for you to browse through as you consider what's appropriate for your applications. We know that this webinar has a lot of information to take in, so we'll definitely provide you with a recording of this webinar, so you'll have a chance to go back and go through this information again. And if you have any questions, of course, feel free to contact us. We do have our contact information here. I want to thank Kristen and Brendon for being on this webinar today and all of you for tuning in. If you have any questions, we know that you have submitted quite a few, and we'll try to submit these questions and collect all of them and make sure that we can answer them after the webinar itself. But thank you again today, and we hope you found this useful. Okay.